that one going-ish. Yeah, so we're going to have to knock this out for the screen. There we go. Oh, that's much better. So, let's start. Any questions you guys have from linear modeling? Linear modeling. The very first homework assignment, anything give you grief. We had to solve for circumference. Let me pull up the actual sheet. So I spelled my own name wrong. No R at the end. All the kids in second grade used to put one there. There we go. Homework sheet. Here she is. Anything in here give you guys grief? Anything in there give you guys grief? All of it. Well, let's start with one of them. Let's start. Harmony, go ahead.
Number 3.
3, E3 or book 3?
Oh, wait. That's a good question. No, book 3.
Book 3. Okay, so it says use the Lind reg. Let's take a look at number 3. Go to the book here. Let's do this. Let's open this in its own tab. That way we have this on its own tab and this one on its own tab as well. Here she comes. All right, number 3. That's okay. You don't have to print the book if you don't want to. I figured it would just save you guys money if I printed it and then put it in a bookstore. There's going to be another middleman involved. I think it's just easier to keep it online. Spider-Man, just keep it a middleman. My son greeted me dressed as Spider-Man a couple days ago. I knew I was in trouble. Okay, so we've got pressure in pounds in various depths, or pounds per square inch in various depths of fresh water. Use the table. Here we got a table here. Does the table relating depth and pressure represent a linear pattern? Do you buy that it's linear, friends? Do you buy? While you think about the answer to that, let me get this ready because I think we're going to need it. I hear a couple yeses.
Yes.
Why? Because it's in the homework for linear modeling. Which is a good answer, by the way. A good answer. Why? Go ahead. What's a less obvious answer, but a more mathematical one, I guess?
There's a pattern.
Say that again.
Pattern in numbers.
I'm sorry. Say it one more time.
Pattern in the numbers.
Pattern. What pattern, Jen, in particular?
It's going up 4.33 each time.
Did you hear that? So the idea is the change in Y, pressure, over the change in X, depth per feet. Now the kicker here is that the depth is increasing by an even increment, 10, 10, 10, 10. That's important. That's important. If that doesn't increase by an even increment, you have to adjust for that when looking at this incremental change. But it is increasing, so that's good for us. So let's look at some different values here. So you've got 14.7 pounds of pressure at 0 feet, so that's at sea level. We drop 10 feet, pressure is now 19.03 pounds per square inch, which is an increase, as Jen said, would you say, of 4.3 pounds per square inch per 10 feet. So from 0 to 10 feet, the pressure, the PSI, increases 4.3 PSI per 10 feet, which is the same as what? 0.43 pounds per square inch increase over 1 foot. So that's from 0 to 10. Well, good. That's from 0 to 10. How about from 10 to 20? How about from 10 to 20 feet? So 10 to 20 feet, the PSI is going to go up again. And it goes up 4.3 feet. Well, roughly. I'm going to approximate, right? 4.3 again. It looks like 4.33 maybe. 4.33. Additionally there as well. So it's up 4.33 PSI again over the course of 10 more feet. Notice it's over 10 feet because it's 10 feet of change. 10 to 20, 10 feet of change. Which means we're once again going up 0.433 PSI for every 1 foot of change. Does the pattern continue?
Yes.
That's what makes it linear. Just like Jen said, a pattern in the constant. What are we actually looking at when we actually do that computation of change in PSI over change in depth? Use a 5-letter word that you know very well from previous math classes, starting with S. There's, I was going to say writing with slope, but you got it. You're counting for the jokes, kids. You got the slope. So change in Y over change in X. So the Y is changing 4.33 PSI for every 10 feet of change. That's an increase of 0.433 pounds per square inch over 1 foot of change. There you go. Make sense? Good. So we buy that's linear. Is the graph linear? Number 2, the answer is going to be yes. How much does the pressure increase for every foot of depth? I guess we just answered it, didn't we? We just it's 4.33 psi for every 10 feet, which correlates to 0.433 psi for every 1 foot. Anybody okay with how I got that? It's a little bit European. Europeans are much better at this because they're comfortable with the metric system more than we are. We stubbornly cling on to our, whatever the hell it's called, imperial system or whatever the hell we call it. But it's very easy to go from here to this. Just move decimals. Both decimals go one place that way. 10 becomes a 1. 4.33 becomes a 0.433. So there you go. So the powers of 10 are wonderful. That's why the metric system is so wonderful. Write a formula that relates the depth in feet to the pressure in pounds per square inch. Love it. Harmony, help me out.
That seemed too easy to me.
Go ahead.
Doesn't it just pretty much give you, it's y equals 0.433x plus 14.7.
That's exactly what it is. It's exactly what it is. What you have to do, since you've agreed that it's linear, you've agreed that the relationship is a linear one. So you know that for a fact. Let me swing the camera a little bit so we're looking at the work we've done over here. Okay. You agree that it's linear, and we've essentially found the slope, which is 0.433 psi per 1 foot. So there's 2 variables at work, and the variables at work are depth in feet and psi per foot, essentially. So let's call x that depth in feet, and y the psi. You know what? Do you want to use different variables? Do you want to use like d and p for depth and pressure? Would that make more sense? I think so, right? Let's call big D the depth and pressure, or the depth in feet, and we'll call p the psi at that given depth. Do you want to use function notation? You want to use p of d?
No.
Do you want? no for p of d. No for p of d. P. No problem. So you've got p as a function of d. So essentially what you need to have are 2 things. You need to have the slope that governs the relationship, and then the initial value when you're at a 0 depth, the y-intercept, or in this case the p-intercept, which would be where d equals 0. But we already have that from the data point. D equals 0, or excuse me, p equals 0 when the pressure is 14.7. I mean, that's when the depth is 0 and your pressure is 14.7. That's your p-intercept. So putting all this together with the slope that we have here and also here, we know that your pressure is going to be a function of 0.433 times the number of feet, which is going to be d. That's the relationship in the slope that we just came up, which makes perfect sense. The ratio of pressure to depth is 0.433. I'll look that right here. But then we have to have that initial when d equals 0, which is the 14.7 pounds per square inch. So there you go. We could also run a linear regression on the data. You could also go L1, L2, and run the whole thing through that way, and run lin reg. But this, I mean, since we had already done the analysis of 1 and 2, it makes sense just to get it off the data here. Did anybody run lin reg on this bad boy to get the data that way? It works just fine. Exact same equation. Exact same equation. It behaves itself. Yeah. Assuming, I am making an assumption, do those actually change exactly 4.33 each time?
Yes.
Literally, yeah. Yeah. Because liquid, I believe, I'm playing physicist here, which I'm not a very good physicist, but I think that's why they use hydraulics in things like brake lines, because the pressure is relatively, it's a non-compressible liquid. So in other words, as you apply pressure, it doesn't compress the liquid. The pressure is constant, I believe. I'm seeing some nods, which...
It's true.
So that's why we're using oil, not necessarily water, but oil.
Well, actually, well... Like,
could you use water too, maybe?
You could, but what the problem is...
It would freeze.
Well, that too, but what will happen is that it'll actually rust the lines, that's why. But in cases of emergencies, people have actually used water instead of hydraulic fluid.
In things like brake lines or heavy equipment?
Yeah, but it's like more of a military worst case scenario.
Of course, well, it makes perfect sense. You usually would be able to go get more oil if you need that. Yeah, unless you're in the middle of the desert, in which case you wouldn't have water anyway, I guess. Yeah, so anyway, there you go, a nice consistent change there. Now this is interesting. Check this out. Look at the next one. Seawater. For seawater, depth and pressure are related as follows. And it says it's almost exactly the same, except look at the pressure is a little bit greater per foot. 0.445 versus 0.433. So this salt added to the water increases the pressure just a smidge in pounds per square feet. 14.7 is still the same. Why would 14.7, why would that be the same for both of them? See the y-intercept down there?
This isn't like before you get it under the water, because it's sea level.
You're at sea level, which essentially you're also at there. You're at zero. You're sitting on the top. You haven't submerged yourself into either one, so that's atmospheric pressure, if you will. That's before you actually have the water acting on you as a pressurized force. Cool? Is that fair? Yeah, ish. Anything else in here? Give you guys grief. Take a look. Let's scroll down. All right, so let's go back to the homework sheet. Come back to book 2. So that was number 3, I guess. I guess we kind of did 1 and 2 for that one. Any of these in here? Give you grief? Besides 3, obviously. Yeah. Anything down here?
E3 was a little confusing.
E3 a little confusing? Let's take a look at that. Thank you, Matt. Yeah, be brave in here, friends. Be brave. If something's not making sense, throw it out here. Gotta switch to blue ink because I'm out of black ink right now. All right. Let's take a look at E3. Sorry, YouTube. Regularly scheduled program will resume. Okay, so analyze the cross-sectional area of the tree. That is the area of the circle that would be left at the top of the stump if you cut the tree down, making an assumption that the tree is circular. I mean, it's circular-ish, but I'm going to treat it as if it's a perfect circle. That's okay with you guys. Using the following formulas, show me why the area of a circle is equal to the square of its circumference divided by 4 pi. So I want to establish that formula right, I can't draw a box around it, but that formula right there. Okay, let's go to that sideboard. Let's have this one set up. Let's swing this one over here. There we go. So I want to prove that. And here's what I know. Number 1, the circumference of a circle, pi times the diameter. Tell me, what is a circle? What is the mathematical definition of a circle? I mean, you know what it looks like. You know what it looks like. Ish. What is, I mean, how do you create one of those things? If you had to draw in a precise circle, what kind of tool would you use to do it? Good, a compass, pointy end, drawy end, comes off at an angle, stick the pointy end into whatever you're drawing, trace like this, and eventually you swing around and you end up with a circle, right? So you've got this thing which is called a what? Remember what this is called? That's a radius. What's this? Which is what? Yeah, it's 2 of those bad boys all the way across. So there's your diameter all the way across the circle. We like diameters. We mentioned in the field, military, kind of in the field. Engineers like diameters more than radii when they're doing work. That's why I like this formula, this whole idea of using pi d, and then for the area of a circle, pi d squared over 4. Most of you don't remember, or maybe you've never learned this formula for the area of a circle, because people learn what formula for the area of a circle? Pi times the radius squared. Engineers can't stand this formula. Think about why. Suppose you're out in the field, you've got a big pipe, and you're trying to figure out the flow through that pipe. In order to know the flow through that pipe, you have to know the cross-sectional area of the pipe and also the speed at which the fluid is actually going through it. So you have to figure out the area of the pipe. So here's this big pipe sitting in front of you, big pipe. And I need to get a precise measurement on how much area this thing is cross-sectional in. How are you going to find the center of this big hole in front of you? Right, with any kind of precision?
2 diameters.
Well, right, but if you can find 1 diameter, you can get the HCD without having to find 2. Now, I'm not saying you can't do it. You totally can. And you don't even need diameters. You can just use chords, which are just non-diametric segments like that. If you draw that one, and then draw where the midpoints perpendicularly hit each other, that's the center. But then, now you're out in the field, with all these extra line segments, making sure they all line up correctly, it's much easier to use a thing called a caliper. You walk up to the pipe with this caliper, diameter, done. You've got it. Now you've got your diameter measure, and you can calculate anything you need from that diameter measure. So a radius is just too much of a pain in the butt. Is this formula more involved than this one? Yes. It's also easier to use. So we're using it. So Same with pi times diameter. There's a circumference formula, 2 pi r, which hopefully makes perfect sense. 2 radii is a diameter. So that hopefully makes perfect sense. Just like, I'll put it back up here again, pi r squared hopefully makes sense too. A radius is half the diameter. So if you square half of the diameter, d over 2, you'll get d squared over 4. D squared over 4. So that's where that comes from. And that's where that magical 4 that's in that overriding formula up there comes from, that fact that you're squaring a half to get a fourth. Ish? Ish? Okay, good. So we'll use these because these are engineers' friends. Where's the circumference? Where's the circumference? It's a distance around, Renee. It's a distance around, Jen. So if you start here, go all the way around and end up back here, that's your circumference. And the beautiful relationship between the distance across the circle and the distance around the circle is that there is a constant ratio of this to this. And that magical number is called pi. That is the ratio of the circumference to the diameter. If you measure this distance and divide it by this distance, you'll always get 3.14152. No matter how big the circle, it increases proportionally. As the circumference increases, the diameter catches up proportionally. Totally rad. Totally rad. It's called pi because before it was called circumference, we called the distance around anything what? What word do you often use when you walk around the outside of something and you take the measurement? Perimeter. That's why the word pi is used, because it's the P sound in Greek. So it's perimeter for pi. We just kept it when we changed it to circumference. You'll useless trivia for you. Make a bucket of bar sometime. Anyway, our job is to come up with that formula for the area of a circle using in terms of the circumference. So here is circumference in terms of diameter. Here is area in terms of diameter. We want to get the area of the circle in terms of its circumference. So in other words, we forgot our calipers, but we're out in the field with a flexible rope and a tape measure. We can wrap the rope around the pipe, right? And then stretch that rope out and lay our tape measure down and get that circumference measure and figure out the area from that. We don't have the right tool to get the caliper measure. So we need to use that formula, A equals c squared over 4 pi. That's what the formula is. I want you guys to understand why it works. So in other words, we got to put this stuff together somehow. We got to put this stuff together somehow. So how are we going to do it? What do you think? How are we going to do this? What do you think? You have to think back to your algebra classes now. And if this feels unduly annoying, the next project will help with the steps. So if some of the steps we do right now don't feel 100% solid, your project, which is due next week, really helps you through some of these steps. So I want to get this area of a circle. I want to get that, but I don't want it equaling pi d squared over 4. Area equals pi d squared over 4. I don't want that. It kind of looks like that. See, area. 4, that's good. This is the problem. I see a d squared here, and I see a c squared over pi here. So there's the inconsistency, right? What I need to do is, I need to get from here, through a series of steps, to get to c squared over 4 pi. So the 4 can stay. The 4 can stay. But I'm going to have to get the pi switched up, if you will, up to here, or excuse me, the pi switched down to the bottom, and this d squared's got to go away. So in other words, I need a relationship between that d and that c, preferably involving pi that I can exploit. Do we have such a relationship that involves both d and c? Exactly. We've got it right here. We've got this right here. This d that's right here is the same d that's right there. So I think we should use that. I think we should use that. I would like to move this around a little bit if it's okay. Because this doesn't have just d on one side. It's got pi times d. Is it cool, my friends, if I divide both sides by pi and get c over pi equals d? Is that legitimate, first of all, what I just did? Am I allowed to do that? Okay, I like that equation better, actually, because that's actually what the diameter is. It's the ratio of c to pi. I like that a little bit better. I like it a lot more for this problem, because now this d that's down here, this d that's right here, is the same as that d that's right there. So this is d squared, though. This isn't d, it's d squared. Can I square both sides of that? What do you think? If I did, what would I get? I'll do this side, d squared. I'm done. What would the left-hand side look like if you squared both sides? C squared over pi squared. C squared over pi squared. Legit, completely. You squared both sides of an equation. Legit. If this equals this squared equals this squared. Fair enough? All right. Now this d squared that's right here is the same as this d squared that's right there. Tell me your name one more time, my friend. Amy said something earlier. She said, why don't we just plug one thing into the other thing? I think we should do that right now. This d squared is that, and that equals this. So my vote is we replace this d squared with this c squared over pi squared, since they're equal to the same thing anyway. So this is really equal to, that pi is still there. I haven't touched him yet. We're going to deal with him momentarily. Times d squared, which is this stuff, over 4. Anybody feeling a little bit sick?
Yeah.
Tell me why you're feeling sick. Be more specific than all of it. Give me the first piece that made you feel sick.
How do you know what to do?
You have, this is where I like this problem because it calls on your previous math classes. This is, if I had to guess, I'm guessing the middle to end of math 60 for a problem like this. You have to look at where you're headed. You're headed, Renee, to get an equation that has an A on the left side and a C and a bunch of other stuff on the right side. We start with an equation that has A and D. So I have to somehow turn D into C, which means I have to have an equation that has D and C together, which I do up there in the number one there.
Okay.
That's the quick and easy answer. I'm not saying that's going to make perfect sense right now. I'm saying that's why project number 1 is going to help you guys. Because that's going to, in case this is going by, I like the fact that we're taking our time in doing this, but in case this is going by too quickly, that first project will really help you out with kind of breaking it down step by step. Good question. Thank you for that. Tell me your name again. Tiffany, thank you.
I worked on projects where it seems a little bit more understandable than this.
But the thing is the steps you're doing in project 1 are the same steps you're doing here. I'm just not listing them all out. I'm doing them verbally, but I'm not writing down each one like I did before. That's why the project's 8 pages long, and this fits on one board. Right? I was trying to answer Renee's question in general, not for a specific problem like this, but the idea is if you need an equation that has A and C in it, you've got to get rid of the variables you don't need and replace them with the ones you do need. Cool so far? Now we start cleaning up. Let's make this look like this. I got my C squared. I'm happy. Got my C squared, happy. Got my 4, happy. I got way too many pies, though. Way too many pies. We clean up some pies. What do you think? Mathematically. Why can I do that? Tell me your name.
Holly.
Holly, why can I do that, Holly? Go. I love it.
They cancel each other out.
They do, don't they?
And then you have one pi left.
Check this out, friends. Pi times c squared over pi squared.
Yes.
So this, say it, Harmony, say it.
Cancel each other out.
Okay, good. Really, when you see pi, you think of this from previous math classes. What that really means is, whoops, the top came off. There we go. It's pi over 1. You use this without thinking about it most of the time. So if it's pi over 1 times c squared over pi squared, really there's one factor of pi up here and 2 factors of pi down here. So one of these will divide off one of those remaining, leaving one behind. Fair enough? So now what you have left is you've got c squared over pi all over 4. This is indeed equal to this, but you might not buy y. Now we're going to go back even further than math 60. Okay, very further than math. And this might throw you for a loop because you've been using it so long, you've committed it to memory, but you don't recognize it when it's in variable form. Check this out. Put the screen up for a second. So, what is 1/2 divided by 2? What is 1/2 divided by 2? It's 1/4. Why is it 1/4? Give me 1 or 2 reasons as to why it's 1/4. Is it Ben?
Yeah.
Go ahead, my friend.
I don't know, you have half and you divide by 2.
You take a half. Imagine this as a picture. You've got a half of something, so you've got that half. and you're dividing that half by 2, which takes away half of the half, which results in the quarter. That's a visual way of looking at it. Tell me your name, friend.
Gabe.
Gabe, that's right. Go ahead.
You can write it in a different form instead of over. You can actually do 1/2 divided by 2.
Divide like this?
Yeah.
Okay, I like that.
And to get to multiplication, you flip and multiply. So it's 1/2 times 1/2.
Remember this? Division by a number is same as multiplication by the reciprocal. That's a rule. What Ben did was he came at it holistically with the actual image. Love that, by the way. Gabe's question, or Gabe's procedure, is to put multiplication, remove the division, create multiplication to make it 1/4. Love that, by the way, too, Gabe. Thank you for giving us a formula for the visual. Very, very nice. One more time, your name?
Kate,
Kate, thank you.
if you take what you originally wrote, the 1/2 over 2, and you just scoot the 2 down with the other 2, that's 2 times 2, and somehow make it 2 times 2, and then that's 4, and then you end up with 1/4.
I love everything except the